We're going to take a look at problems 17, 18, and 19 on your energy review. Number 17, a skier slides horizontally along the snow for a distance of 21 meters before coming to rest. The coefficient of kinetic friction between the skier and the ground is 0.050. And initially, how fast was the skier going is the question. We're going to take a look at our work energy theorem, which is the change in kinetic energy equals the total work. Now the kinetic energy at the end of the problem is 0 because the skier comes to rest. So that's why this is canceled out right here. Ke2 goes away. So that's going to leave me with initial kinetic energy equals the total work done. And the initial kinetic energy is 1/2 mv squared equals the force of friction times distance, because the force of friction is the force doing the work to make the skier stop. Now notice I drew the picture over here where I've got friction is slowing the person down, normal force is up, and gravity goes downward. You should know that the force of friction is equal to the coefficient times the normal force. That was one of our equations from the forces section. Well, the normal force is up and force of gravity is down, so that means that the normal equals force of gravity, so I can rewrite friction as mu times mg. The reason why that's so important is when I look at this part of my work energy theorem equation as I'm working through it, I see I've got 1/2 mv squared equals force of friction d. I don't have what the force of friction is, nor do I have what the mass is. So I'm stuck unless I plug in for force of friction mu, which I've got, times m times 9.8, or g. When I do that, I've got m on both sides of my equation, and it cancels out. And then I just have to do a little bit of algebra to solve for the initial speed. So I'm going to divide 1/2 or multiply by 2, and now I have 2 mu gd over here on the right side. Take the square root to get rid of the squared, and I have the square root of 2 times 0.05 times 9.8 meters per second squared times 21 meters for an initial speed of 4.5 meters per second. Number 18. The hammer throw is a track and field event in which a 7.3 kilogram ball, also known as the hammer, starting from rest, is whirled around a circle several times and then released. It moves upward on a familiar curving path of projectile motion. In one throw, the hammer is given a speed of 29 meters per second. For comparison, a .22 caliber bullet, whose mass is 0.0026 grams, which is it's 2.6 grams in the problem, 0.0026 kilograms when we convert. It starts from rest and exits the barrel of the gun with a speed of 410 meters per second. We're going to determine the work done to launch the motion of both the hammer and the bullet. So we'll start with the hammer. The change in kinetic energy of the hammer equals the total work done. It has no initial kinetic energy because it has no initial speed. It starts from rest. So we just have our final kinetic energy equals the work done. So I can just plug in 1/2 mv squared equals the total work, which is 1/2 times 7.3 kilograms times 29 meters per second squared, gets me 3,069.65 joules of work. For the bullet, again, no initial kinetic energy, so it's all final kinetic energy equals the total work done, which is 1/2 times 0.0026 kilograms times 410 meters per second. Don't forget to square it, and that gets me 218.5 joules of work for the bullet. You might think that since the bullet's moving so much faster that it would take a lot more work, but because the hammer is so much more massive, it actually takes quite a bit more work to throw that than to launch a bullet. Number 19, a slingshot fires a pebble from the top of a building at a speed of 14 meters per second. The building is 31 meters tall. We're going to ignore any air resistance, and we're going to find the speed with which the pebble strikes the ground when the pebble is fired horizontally, straight up, and straight down. This is our first conservation of energy problem, and the best thing to do is always draw a picture so that we know what we're talking about, because conservation of energy requires us to look at two distinct points in time. In this problem, I'm going to look at when it's launched, which is right up here with the little person, and when it hits the ground, because that's when I want to know stuff about it, which is how fast it's going. I set up my equation, which is the initial potential energy and the initial kinetic energy, so all the initial energy equals the final potential, the final kinetic, and any energy that was taken out by friction, which is all of the energy at the end of the problem. All the energy at the beginning equals all the energy at the end. Why is some stuff crossed out? Let's take a look. We're going to determine what kind of energy this pebble had at the two distinct points that I care about, when it's up with the little guy and when it's at the ground. When it's up with the little guy, is it up off the ground? Does it have potential energy from gravity? Yes, it does. So I'm not going to cross this out because it has that energy. Is it moving? Yes, it is. It's moving 14 meters per second. So kinetic energy stays as well. At the end of the problem, when it gets to the ground, it's on the ground, so it's got no more potential energy. That's why this is crossed out. But it certainly is moving when it's going to hit the ground, so we will have KE. Sometimes people might think, but it's not moving after it hits the ground. It didn't ask about what happens after it hits the ground. It says as it hits the ground, as it's about to do it. That instant right before it makes contact with the ground. Once it hits the ground, that would be a completely separate type of problem. And since there's no friction or air resistance, we don't have to worry about thermal energy at all. Now I take the things that I've got, the PE1, the KE1, and the KE2, and I'm going to write them beneath here, and I'm just going to expand them into what they are. The potential energy is mgh, kinetic energy, 1/2 mv squared, and kinetic energy 2, also 1/2 mv squared, realizes the initial speed. This is the final speed. I have m in every term, so I can cancel it out just by dividing it. And that gives me GH plus 1/2 V squared equals 1/2 V final squared. We're solving for V final, so I'm going to multiply the half to the other side, multiplying this half by 2, because when we divide by half or multiply by 2 to get rid of this one, 1/2 times 2 makes it go away, and that's why there's a 2 next to the GH. I'm going to take the square root because I want to get rid of the squared here, and I get the square root of 2GH plus V squared. Plugging in my numbers, I get the square root of 2 times 9.8 meters per second squared times 31 meters plus 14 meters per second. Don't forget to square it, for a speed as this thing hits the ground of 28.35 meters per second. Now you might say, wait, we were supposed to solve for 2 other paths. When it's launched horizontally, we just did, but also when it's launched up and down and just straight down. Well, this is the thing. The conservation of energy equation wouldn't change no matter which way we launched it, because all of the energy is always conserved. So my equation would never change, so I don't have to do it 3 times. I know that if I shoot it straight up, straight down, or straight out, or even at some kind of an angle, if I launch it at a speed of 14 meters per second, it will hit the ground with the same speed, 28.35 meters per second, every single time.